Do you see what I'm holding here in my hand? This is my most recent electricity bill. And you know what? Every month it's the exact same thing. I open this up and I get a big old surprise with the amount written on top. I'm ready to do something about this problem, but my utility bill only gives me the total number of kilowatt hours that I used. I want to know how much of that total usage is my workshop versus charging my electric vehicle or my HVAC system. I have no idea. Maybe there are some habits that I can change to reduce my electricity bill. My name is Zach and I'm the Byte engineer. In this video, we're going to tackle this problem by building a whole home energy monitoring system using cheap components. If we break this problem down to its core, really, I just need to be able to measure the current flowing through the wires in my house. Here in North America where I live, I have split single-phase power coming into my house, which means that my outlets measure 120 volts RMS. If I can measure and add up the two currents coming into those phase wires and then multiply that value by 120 volts, that will give me the power that my house is currently using at that given moment. So let's talk about different ways I could measure that current. The first option is to use a dedicated current measuring IC like the ACS712. This one comes in different variants that can measure 5 amps, 20 amps, or 30 amps. But there's a major drawback. I have to break the circuit and insert this in series in order to make that measurement. And that's really not an option for a panel like mine. So I think I have to scratch that idea right off the bat. The next option is to use a clamp meter like this. This is the Fluke 323, and it can measure currents flowing through a circuit without breaking it. The way this works is that anytime there is current flowing through a conductor, it creates a magnetic field. If you bring another conductor within that magnetic field, it will induce a current in that secondary conductor. Let's say, for example, that I want to measure the current flowing through this set of wires. If I close the clamp around the whole set of wires, I'll actually get a reading of 0 amps. That's because the alternating current running through the hot and neutral wires will cancel each other out. If I want to get an accurate measurement, I actually have to isolate these wires so that I can wrap my clamp meter around either the hot or the neutral wires. But there's another major drawback to using something like this. I have to physically read this, and I don't want to have to write down the values every time I measure something. We need something that I can read with a microcontroller, and that's where this last option comes into play. This is a current transformer, and it works exactly the same way as a clamp meter. It has a coil of wire in here, and when I wrap this around a conductor, it will measure the current flowing through that wire. So let's see if I can connect this current transformer to a microcontroller and then read the power usage of this space heater. The current transformer that I'm using is a 2000 to 1 ratio, but since it's basically just a coil of wire, it's going to produce a current, and we can't read that with a microcontroller. So we have to translate that current into a voltage using what's called a burden resistor. So if I draw my transformer here, I need to add a 20 ohm resistor across its terminals. With this burden resistor in place, the current transformer can now produce a small sinusoidal voltage that our microcontroller can read. By using a 20 ohm resistor with this specific transformer, that gives me a 1 volt swing when measuring 100 amps. And that's the perfect amount of swing to stay within the range of a 3.3 volt microcontroller. And that brings us to the next hurdle of reading current transformers with a microcontroller. Since we're measuring an alternating current, we don't want that 1 volt swing to go below 0 volts. So we have to bias our transformer up to the middle of our range. So to do that, I'm going to use two 100K resistors like this that bias our voltage up to 1.65, which is the exact midpoint of our 3.3 volt logic. Now, as that voltage swings up and down, we don't cross below 0 and we don't go above 3.3. The final piece of the puzzle is to add a filtering capacitor to the ADC input. This is going to smooth out any high frequency spikes that we might see. By building this circuit, we can read a current transformer using a microcontroller. So I've gone ahead and I've built this circuit on a solderable breadboard. I'm ready to install the current transformer on the space heater cable, but like I said earlier, I can't clamp this around both wires. I need to separate them. Rather than making any permanent changes to the wire of the space heater, I'm just going to take a cheap extension cord like this, and I'm going to carefully use a utility knife to separate the two wires. This should go without saying, but don't do this with the cable plugged in. Now I can safely plug this in and clamp the current transformer around a single wire. My whole goal with this project is to monitor my electricity use using Home Assistant. If you're not familiar with Home Assistant, it's a really popular smart home dashboard that you can install on your computer or even a Raspberry Pi. I've already got Home Assistant set up and running on a Raspberry Pi, so all I need to do is write some YAML code to upload to this microcontroller to see if we can read the power coming out of this unit. The microcontroller I'm going to be using for this project is the Seed Studio XIAO ESP32S3. This is my go-to microcontroller for building DIY projects in Home Assistant using ESP Home. I've got the microcontroller connected to the Solderable Breadboard, and now I'm ready to add it to Home Assistant. The first thing I'm going to do is click New Device. Now I can click Continue instead of opening ESP Home. I'm given a few options here, so I'm going to click on New Device Setup, and I'm going to name it Test Energy Monitor. Then I need to choose ESP32S3. You can see here it creates a YAML file called Test Energy Monitor. The only thing it contains right now is the API, OTA, and Wi-Fi elements. One thing to note here is that I'm using a secrets file that I have my Wi-Fi credentials stored in. That way all of my ESP Home YAML files can just reference that one secrets file. Now I'm going to click Install, and I'm going to do a manual download. This is going to kick off the compiler, and it's going to take those configuration elements and compile it into a binary. The reason I'm compiling the basic configuration and then installing it on the ESP32 is that once I've got that basic configuration installed on the device, I can actually unplug it and install it wherever it's going to go. Then from there, any updates I need to make, I can do over the air using the Wi-Fi network, which is pretty cool. All right, it looks like it succeeded. It took 139 seconds. Now it's asking me what kind of version of the binary I want. I click Factory Format, previously known as Modern. So this is going to save the binary locally to my computer here. So I'm going to navigate to a folder that I use for these and click Save. There's one extra little tricky step here. My Chrome browser is treating this file as kind of unknown and unsafe, so I'm going to manually click Keep, and that will actually complete the download. Now I'm ready to go back into the Home Assistant environment, and then I'm actually going to click New Device again because it kind of closed that dialog box. And I'm going to open up ESP Home Web, which is an easy browser tool used for loading compiled binary files to an ESP device. And then I'm going to plug in my microcontroller, but I need to make sure I put it into bootloader mode, so I'm going to hold down the bootloader button as I plug it in. That comes up as COM16 on my computer. Now we just hit install, and I'm going to choose the file that I just downloaded. There's a couple of things that you'll want to keep in mind during this setup process. You'll notice that I put it into bootloader mode. If you forget to do that, this won't work. The other thing that you need to remember is to install the Wi-Fi antenna on these boards. They won't connect to a Wi-Fi network without one, and don't ask me how long I got stuck on that before I figured that out. Now I need to power cycle the device, but since I'm moving it over to the other workbench, I'll just unplug it here and plug it in back over there. One thing we need to do before we move on is that we need to go to the device page and then add the discovered device. After I flash that binary and reboot the device, it'll show up here and I can just click Add. And if I want, I can select which area it'll be in, but for now I'm just going to click Skip and Finish. In order to read the current transformer using the ESP32, we need to add a few things to the configuration file. All of this stuff I'm about to show you can be found in the ESP Home documentation. In fact, if I search CT clamp, I'm just going to copy and paste the example here. I just need to change the pin number to GPIO 10, which is the one that I use to connect the sensor. I'm also going to change the update interval to 1 second. This next part is really important. I need to be able to calibrate all of the ADC readings and map them to the appropriate number of amps. So to do that, I'm going to add a filter, and I'm going to use Calibrate Linear. And the syntax here is I want to map a raw ADC value of 0 to 0 amps. I'm just going to guess at this point. I'm going to say 0.6 is going to map to 10 amps. Then we can load this onto the device and then measure the space heater, and that way we can read the raw ADC values and update our calibration. You can actually extend this calibration and give it several points to use. That way, anytime it measures an ADC value, it will look at the calibration table and find that point and then use linear interpolation. Let's go ahead and upload this to our device. So I'm going to click Install, and I'll select Wirelessly Install, and now it will compile it and then send it over the air. I didn't have it plugged in. That's why it failed. There we go. Okay, uploading. All right. Yeah, I make mistakes too, don't judge me. Okay, this is exactly what I was hoping to see. So we've got the logs now printing out to the screen. If you accidentally close this and you need to get back to it, go back to your ESP home dashboard and then find your device. In this case, it's Test Energy Monitor, and I click logs and we'll get the exact same thing. So it's printing out a whole bunch of boot information, which is good. And then the data that we're seeing in that light blue color are the ADC values and what it's mapping to. So if you see the line that says current raw AC value 0.008009, those are our raw ADC values, and we need to map those to what we're measuring. This is the device page. We can see that the current measurement is here, but it's not correct. That's why we need to calibrate it. So let's head over to the workbench. We're finally gonna plug in the space heater. We're also going to use the Fluke clamp meter as a reference to calibrate this device. All right, first I will clamp our DIY current transformer on there, and then I'm gonna turn on the Fluke clamp meter and also install that on here. The space heater is currently off, so it's not pulling any current. The Fluke meter is reading 0.1 amps. And now I'm gonna open up the Home Assistant app on my phone to read our current transformer. It's currently reading 0.14 amps. But let's turn on the space heater and see what happens. Immediately we see the Fluke jump up to 4 amps, but unfortunately the current transformer isn't reading anything. So I've got a problem I need to figure out. I'm looking closer at the wiring and everything seems to be fine. I'm going to check the pinout of the microcontroller just to make sure that I have the numbering correct. All right, so I soldered the output of the current transformer to this digital pin 10 or analog pin 10, but I'm looking over here on the side and it says GPIO 9. So it's digital pin 10, analog pin 10, but the name is GPIO 9. I wonder if that's the problem. That's an easy fix. I can just go in the configuration file, update the name, and then reflash it over the air. In addition to changing the GPIO number, I also added an auto attenuation line. So let's open up the Home Assistant app. It is currently reading 0.03 amps. Our Fluke is reading 0.1. Let's turn on the space heater and see what happens. Okay, so the Fluke jumps up to 7 amps, and the Home Assistant is reporting 1.3 amps. So we've got a change here, which is good, but that linear interpolation is off, so we need to calibrate it. So what I'm gonna do is I'm gonna let the space heater settle into its steady state and then measure that current using the Fluke meter. So right now it's at about 10 amps. Let's go check the logs and see what the raw ADC value is. So I'm getting a raw value of like 0.102, So let's close this and we're gonna change the linear calibration. Instead of 0.6 mapping to 10 amps, we're gonna do 0.101. Okay, so that update went live and now the readings are really close. The Home Assistant is reporting 10.3, 10.4 amps, and the Fluke is reading 10.5 amps. That is really close. That's good enough for me. I think if I really wanted to get this dialed in, I could find some heavier loads that are more than 10 amps and add those as calibration points in my linear interpolation. But for now, I'm gonna move on, and I think I need to take this off of a solderable breadboard and design a full-fledged PCB. All right, so I've spent some time designing a schematic and a PCB layout. Here's what I came up with. This circuit should look very familiar, but on the left-hand side, we have an audio jack. The reason I added that TRS connector is that most split core transformers come with an audio jack like this, so it just makes it easy. You can see here that I've got the 20 ohm burden resistor, as well as the two 100K resistors, which bias the circuit up to 1.65 volts. For this circuit board, I actually made 3 copies of this circuit because I want to attach 3 current sensors. So here's what the full schematic looks like. I've got 3 identical copies of that current transformer circuit, and then the output of those connect to 3 ADC pins on the microcontroller. The PCB layout is actually pretty compact. I've got all 3 TRS jacks lined up, and then the microcontroller actually snaps on top of the center TRS jack. This is what the board will look like in 3 dimensions. So let's go ahead and get these boards made using DK Red and assemble them. The assembly of the PCB came together perfectly. I went ahead and I tested everything, and out of sheer luck, everything worked perfectly the first time. I think that might be the first time that's ever happened when I've designed a PCB, but I got lucky this time. Now I'm ready to install the current transformers inside my panel. Working with electricity inside a utility panel can be very dangerous. If you decide to take on a project like this, I recommend hiring a qualified electrician to do this work. I'll be turning off the main breaker before opening up the panel. Even with that main breaker turned off, there is still high voltage at those main phase wires. Obviously, once I turn off this breaker, all the lights are going to shut off, so I'm going to connect these overhead lights to this tool battery inverter. One thing that's really important to note is to use a current transformer that will fit comfortably around the wire that you are trying to measure. You don't want to use a current transformer that won't close all the way around the wire. Also, you should never close the current transformer without the burden resistor in place. That means that I won't be closing these current transformers until I have them plugged into the PCB. If opening your electrical panel feels a bit too daunting, don't worry. Most modern meters actually broadcast real-time data wirelessly. You won't get the granular detail of individual circuits, but if you'd like to see me attempt to intercept those signals using an RF receiver instead, let me know in the comments and I'll add it to my project list. Now that I've got those installed, I've turned the main breaker on and I'm going to plug in the microcontroller, and hopefully it will connect to Home Assistant and we'll be able to start reading the current running through these phase wires. Okay, so it connected, and I'm going to measure the one on the left using the clamp meter. And it is currently reading 28.5 amps, and Home Assistant is reporting the same thing. So that's working. Let's go ahead and measure the other one. That one's reading 21.2, and Home Assistant is measuring the same thing. So this is working. We could stop here. I could design a 3D printed enclosure for this, mount it to the wall, and we'd have a home energy monitoring system. But this setup isn't really that different from what my electricity bill tells me. Fortunately, I have a secret that I haven't let you in on yet. I designed this PCB to be stackable. I'll remove the microcontroller and I'll stack on 6 more TRS jacks. This gives me a total of 9 current transformers that I can plug in and read. I'll use 2 for the main phase lines coming in, and then I'll use the other 7 for individual circuits that I want to measure. Within Home Assistant, you can actually create a downstream hierarchy so that the current transformers that are reading the individual circuits will feed into the 2 main current transformers. And of course, I designed a 3D printed enclosure that I'm going to mount to this wall here. So let's get this installed and button everything up. As one last finishing touch, I laser cut an acrylic cover for the home energy monitor. With the panel all closed up and the ESP32 sending data to my Home Assistant, the mystery of my electricity bill is a thing of the past. This is Home Assistant's energy dashboard, and for the first time, I'm seeing my home's detailed energy use in real time. The 2 main CT clamps that I installed at the top of the panel will give me the overall power that my house is using. But the real value comes from being able to break down individual circuits. Because I installed 7 additional current transformers, I can see exactly when the well pump kicks on, how much it costs to run a load of laundry, or how much power my workshop is using when I'm down here using tools. Home Assistant does a great job of breaking down which loads are using the most electricity. For example, today it looks like my EV charger was the biggest use of electricity. But if we look at the data for yesterday, which happened to be laundry day in our house, we can see that my dryer was the one that used the most energy. I love all the different ways that I can visualize this data. For example, I can see that I have energy coming from the grid and it goes into my home, and then Home Assistant will actually break it down to which rooms and areas in your house are using the most electricity. Here in my basement, I've got my utilities set up, and that's where I'm measuring all those circuits inside my panel. With these current sensors in place, I was able to discover that I have a humidifier plugged into my basement that's randomly kicking on and off and driving up my electricity bill. With Home Assistant, I can just add some humidity sensors and only turn on the humidifier when it's actually needed. If you decide to take on this project, my biggest piece of advice is to get yourself a clamp meter like this so that you can calibrate your sensors and get the most accurate information out of them. I started this project because I wanted more transparency from my electricity bill. And I was able to solve that problem by building custom hardware that integrates with Home Assistant. I plan to use this information to create automations and also adjust my habits and save myself a lot of money in the long run. As always, you can find the schematic and design files for this project on maker.io. My name is Zach and I'm the Bite-Sized Engineer. Thank you so much for watching and I'll see you next time.